about QC and QA, they're not the same thing. So a recap of actually 2 weeks ago. So standards are pure, weighed out, and known concentration of your desired analyte. And those 3 little catchphrases should be embedded into your soul: pure, weighed out, known concentration. And calibrators, on the other hand, are traceable to the National Institute of Standards, and usually contain multiple analytes, because that way you only have to put 1 calibrator onto the instrument instead of 50, that are used to calibrate the analytical instruments. But once again, they're still weighed out, known concentrations. Purity is obviously questionable because there's a mixture of them now. But you can use single point standards or multi-point standard curves to calculate the concentration of your unknown in an analyte, of concentration of the unknown analyte in your sample. So to do the single point, you take the absorbance of your unknown times the concentration of your standard over the absorbance of the standard. And if you have multiple standards, it's best to choose the standard that is closest in absorbance to your unknown, just so you know you're closest to where you are. And then you have your little standard curve here. This is a perfect one because this is fake data. So that's what it should look like. Signal versus concentration. You can flip them if you want. If you do it this way, your equation will just be plug in your absorbance for X and solve it. You just plug it in, plug and chug. Whereas if you do it the other way, you have to like solve for X, and it's a little extra step. But graphically, I think the other one looks better. So all depends on you. All right, so analytical sensitivity and specificity. So analytical sensitivity, that's the smallest concentration of your analyte in a sample that you can accurately measure. All right, so this is basically as low as you can go and still know that you're being accurate. Analytical specificity, on the other hand, is the ability of your assay to determine specifically the concentration of your target analyte in the presence of an interfering substance. So there, for example, there are hormones that have this, all have the same alpha chain, like alpha unit, but they have different beta units. So if you have an assay that looks at the alpha unit of a hormone, you're going to have a lot of interferences, and it's not going to be very specific. So you would then design an assay that looks at the beta unit, because that's unique to each hormone. And then that would make the assay more specific. So in the presence of an interfering substance, how good are you at actually measuring your analyte of interest and not something else? And to be clear, these are different from clinical sensitivity and specificity. We're not going to talk about those a lot, but clinical sensitivity and clinical specificity have to do with the ability of an analyte to determine if someone does or does not have a disease at a certain cutoff value. But we will talk about that in a different class. But they are not the same. So just so you know, there's a difference. All right, so then some other nice definitions. We have the analytical measurement range, or the AMR. And this is the range of analyte values that a method can directly measure on the specimen without you having to do anything to the sample. So you're not concentrating the sample, you're not diluting the sample. This is literally, does it fit on the standard curve? All right, that's the analytical measurement range. The clinical reportable range is where you can now mess with the sample so that you can expand the actual concentration of analyte you can measure accurately. So this is where you can dilute your sample. This is where you can concentrate it down if it's already has a really low concentration, so you can make it higher concentration. So it then fits on your standard curve. So this is things that ways you can manipulate the sample to basically increase what concentration you can report. Because there are certain analytes, especially like enzymes, the assay maybe is only linear to like 200 units per liter, but in a disease state, it can bump up to 5,000. So it's necessary for you to be able to dilute it to get into the clinical reportable range so that you can actually say, okay, this is how sick your patient is. All right, and then the limit of detection, or the LOD, you can tell that we like abbreviations in the clinical lab. Ain't nobody got time to write all these out. The lowest value that significantly exceeds the measurements of the blank sample. So that's basically saying if I took a blank sample and measured it 20 times and recorded the measurement or signal at each of those times, that's kind of what my blank is. And then the clinical limit of detection is the value of concentration that I can tell apart from that blank. So we'll do some little arts and crafts time here. So say this is concentration, this is your absorbance, and your blank is over here like this, all your little absorbance values They have some noise. It's not all just one value over and over again. Whereas your sample of interest, it would have to be where it doesn't overlap. It's above that, because if it's over here, you can't really tell if it's blank or if it's not. So you have to be above that noise level that's the blank is at. Does that make sense? All right, so whew, this is fun. We have hidden markers down here. And that's so you can reliably detect that there is actually analyte in your sample. This is it graphically. All right, so someone who's not me made this graph. So this is your noise. That's basically if you keep measuring your blank over and over again, what's the noise level? And then you have your limit of detection, which is above the noise. And that's where you can just say, I have sample or I have analyte. It is in there. I can't necessarily tell you how much accurately, but it's in there. The limit of quantitation, or the LOQ, is the concentration of the analyte where you can go like, I can reliably tell you how much is in that, how much analyte is in that sample, because there's enough in there that the precision and all that works out. And then you have your analytical measurement range, which is the linear area of your standard curve. Then you have your limit and that ends at your limit of linearity. This is where you lose your, right before it starts to taper off. And then if you are allowed to dilute your sample and stuff, you can dilute it back down into this analytical measurement range, and that then expands your clinical reportable range. Even though the standard curve shape hasn't changed, you're just now allowed to manipulate the sample. All right, so let's talk about error. It happens. No one is perfect. If you ever watched Jurassic Park and like the little droplet of water that rolls down his hands different ways, that's the lab. It's stochastic. Chaos happens. So even if you do the same thing every time, just things happen. So error happens. So there are two main types of error. There's systematic, which is in the system. It's not really something, it's not really your fault necessarily. But it's in the system, so it's always going to be there. Whereas random error changes every time you do it. So it's important for us as laboratorians to reduce error whenever possible to make sure that we're reporting as accurate of results as possible, so that, because doctors are making medical decisions based on our lab values. So there are ways to quantify and track error, which is where quality assurance and quality controls come in. And then we can identify sources of error and help to improve them so that we don't have them, because our job is to make sure there is little error as possible. All right, so systematic errors. So these are reproducible inaccuracies that are consistently in the same direction. So that's basically, it's always kind of the same. It's always going to be slightly high in this system, or it's always going to be slightly low. So whatever that is causing that error, it's in the entire system, it's going to affect everything kind of equally. So the magnitude of that inaccuracy is measured by the bias. So you get these cool little bland Altman plots. You will not actually, I'm not going to expect you to be able to like use these. I'm just letting you know that these exist in the world right now. And you can basically have the mean of your, say, two different methods that you're comparing. And so you take a sample and you measure it on both methods at the same time. You get slightly different values. You average those together. You plot that mean over a range of concentrations, and then you plot what each measurement actually was. And then you get this nice little bias plot. And you can, so you can actually see like, oh, hey, assay A is always higher than assay B, or it gets proportionately worse the higher the concentration goes. So this can be caused by changes in your reagent or calibrator lot. This is why a lot of times labs will buy a lot for the entire year. So that way I don't have to deal with this. It's just, this is our lot for the year. We're not going to mess with it again. You can have put in the wrong calibrator values into the computer. You could have prepared your reagents improperly. Say you did a one, like dash, no, slash 100 dilution instead of a one in math. You did a 1 colon to 100 instead of a 1 backslash to 100. So you messed it up. So that could affect things. Your reagent or calibrators can deteriorate. They might not be stored properly. Your pipettes might be misaligned in the instrument, or you're not very good at pipetting. That would be random though, unless you're always slightly higher, in which case it's a tech problem. So you are the system in that part of the system in that problem, and you're always wrong. This happens in real life, that like people have slightly different ways they do things for some of these manual methods, and like everyone's slightly different. variation in temperatures, your light source is deteriorating, or how different texts do things. So just changes. This is why there's usually an SOP where like, we want you to do it exactly this way. Don't go rogue, because it matters. All right, so random errors on the other hand. So these are just statistical fluctuations. They can be on either side of the mean. And this is just due to the precision limitations of the assay. So this is just randomness. You can't control it. It just happens every time. It's just the way life is. So you can quantitate these though by the standard deviation. This is a nice little Gaussian distribution or bell curve. And one standard deviation is here in this dark blue, and that covers about 68% of all values that you measure. That's going to be one standard deviation away from the mean, whereas 2 standard deviations of the mean is going to cover 95% of just random error. So 95% of the time, you should be within 2 standard deviations from the mean. And then the 3 standard deviations, which is this light blue, 99.7% of values, just statistically due to random error, should fall within 3 SD. So for our purposes, usually we say something is out of control or has failed if it's outside of 2 SD, because that is a good enough cutoff that we're not going to get flags all the time that something's failed, but it also is sensitive enough that we're going to catch something that's gone wrong. You don't want to have to troubleshoot everything all the time. No, you do not have time for that. Okay, so you want to be like, okay, something has actually gone wrong without like having to go through way too many things. And then you have coefficient of variation, which kind of just normalizes to the mean. So you can look at like apples and oranges together, so they both look like watermelons. Essentially, you just normalize to the mean. It's fun times. All right, so causes, air bubbles, you can't control that. Improperly mixed reagents, syringes, pipette tip wasn't on perfectly. That happens. You might have a clog. The power supply can fluctuate. You cannot control that. Like, that just happens. All right, so all this combined comes up with the accuracy, precision, and reliability of a method. So the degree of fluctuation in the measurement is indicative of the precision of the assay. So precision is basically the ability to get the same value over and over again. It's not necessarily the right value, but you get it over and over again. So if you're looking at like a dartboard, you are extremely good at clustering them together closely, but you're not on the bullseye necessarily, but you're really good. You really got really tight cluster. So that's precision, hitting the same value over and over again. Whereas accuracy is how close are you to the true value. So in this case, on this one, this is high accuracy. So they're close to the bullseye. They're not particularly clustered together very well, but they are close to the true value. And you're like, yay, we're getting the right value. So this is how close you are to the true value. And then reliability is the combination of precision and accuracy. So in the clinical lab, we are aiming for reliability because we want it to be precise and we want it to be accurate. So this is when it's clustered on the bullseye, very close together. This is when you get to go to the Olympics and win a gold medal. All right. You're not going to win a gold medal with this. You're not going to win a gold medal with this. This is what you want. If anyone watched archery in the Olympics, it was insane. All right. I love watching the Olympics. All right. So total error. This is the sum of the random error and the systematic error. So you combine those together. And so that combines the inaccuracy that comes from the systematic error and the imprecision that comes from the random error. And this is basically the bottom line of how much error there is in your assay. So for most analytes, the Clinical Laboratory Institute, CLIA, we just call it CLIA, publishes the acceptable total allowable error for an analyte. So, and this can vary based on the analyte and kind of how they write it. So for example, we're going to do chemistry values because I teach chemistry, so I get to choose. So for albumin, which is a protein in the serum, you have your target value, which i.e. your true value, and your acceptable is like plus or minus 10%. So the bigger the concentration is, the wider the amount of inaccuracy is acceptable because it's a percentage of the concentration. Whereas with creatinine, this is kind of fun. They have either 0.3 milligrams per deciliter or plus or minus 15, and it's whichever is greater. Because when you get down to these really low concentrations, 0.3 might be that might be If it's just 15% of a really small concentration, that is not a lot of wiggle room. So if you have that 0.3, that gives you a little bit more wiggle room at those really low concentrations, because otherwise you're trying to hit an extremely tiny little target with a method that's not that accurate. So that's why you get that whichever is greater, so that you get a little bit of a bigger window to try to get your assay into. And then you have HCG, and this is like plus or minus 3 SD. HCG is kind of one of those, you're pregnant or you're not, so you get a bigger range. All right, so reference intervals or reference ranges, it's kind of tomato, whether you call it a reference interval or a reference range. So this is the range of an analyte that's determined to be normal in a population of healthy individuals or some other defined population. So in general, for the most part, it's just going to be like a healthy population. You might have a reference interval for males versus females or children versus adults, but whatever your healthy population is, that's your reference interval. And that's basically, if you fall outside that reference interval, that indicates you have some type of disease state. So they can separate it by sex, age group, stage in pregnancy, physical condition, race if needed, because there's some analytes that vary more by race than by others. And to do this, you have to measure a lot of healthy people. So these are your reference individuals. And the magic number for this is 120 people. That's where you kind of get the statistical significance to determine what's normal. So you measure the concentration of your analyte in 120 seemingly healthy people. And then you take whatever 95% of them fall into. Because you don't want to be like all inclusive, because then you might miss sick people on either end. So you want to kind of cut off that tail so you can catch the sick people. Because even though your people look healthy, you don't know 100%. So you want to have a little bit of a wiggle room. So you cut it off at 95%. And that is your reference interval. All right, so now we're going to talk about QA. Ooh, phones. So how will we know if we perform a test correctly? So this is why when you're doing testing, you include a specimen in your test where you know what it should be. You include a known concentration. So this is what quality control material is. And you compare your assayed value with the expected value. And if it's too far off, you go, something has gone wrong. I need to look back and figure out what has gone wrong and how I can fix it before I can release my patient results, because I don't know if it also went wrong in my patients. So this is where quality control testing comes in, and it's the process for verifying performance of your test system over time. So it's basically like you're constantly checking to make sure your test system is still working. So you can assay the control materials in the same way you assay the patient, and then you compare it to the expected values for acceptability. And then the frequency in which you have to do this is based on CLIA rules. So sometimes it's every shift, sometimes it's just every time you some things that you don't run very often, you just do it whenever you're going to run it. And then other things, it's like every 4 hours because it gets sketchy really quick. And then how many levels, you're usually choosing a high and a low, or a positive and a negative. And usually those high and lows are at medical decision points, because you want to be the most accurate at the concentration where a doctor is going to be making a decision. All right, that makes sense, right? But if you're in the middle, it's like, okay, well, you're still in the middle. But if you're at okay, they're getting diagnosed with cancer versus not, you want to be accurate at that cutoff. So usually your QC is at that cutoff. All right, so quality assurance, this focuses on the prevention of defects. This is more of a system look at things, where you look at your entire system, your entire lab, and go, okay, where can errors happen? How do we prevent them? And it basically just manages the quality. Whereas quality control is kind of a subset of quality assurance. This is you actually on the ground, making sure that everything is working. So this is looking at the results and going, I'm good. The assay is working. I can confidently release my patient results. So this is a product-based approach. So if something goes wrong, then you go in and be like, okay, I need to fix something. So it's kind of reactive. Whereas quality assurance is proactive, because you're trying to prevent something from happening in the first place. All right. So quality assurance is this continuous process where you're identifying quality problems that could potentially happen, even if they never happened before, and determining some criteria and standards in relation to monitor it. And then within quality assurance is quality control, and that's where you're actually monitoring if there were errors that happened, and then reacting and making changes and correcting things. All right, so quality assessment covers all aspects of ensuring high quality results, and then looking at all areas of the test system to look for problems. So the test system includes things like your reagents, your technicians, your equipment, your instruments, the lab space. I worked in a lab where in the summer, it was really humid and that messed with our blood bank instruments because the humidity messed up our gel cards. So your system even includes like the environment and the season sometimes. So that was obnoxious when that happened. We had to spin the cartridges before we used them. Because I don't know, it's just the humidity messed with things and it would like cause everything to like fail more often. So we had to like spin all the cards before we used them. It's just added an extra step. It was annoying. Don't recommend it. Don't live in the South. It's got tornadoes. You don't want it. All right. So it can include things like policies and procedures, maintenance, safety programs, specimen collection and handling guidelines, QC testing, proficiency testing. We'll learn about that in a few slides. Laboratory training and competency assessments. You get to experience one of your first competency assessment today, where we basically check, yes, you're doing it right. And that's what you're going to see in the lab, where you have to do annual to semi-annual competency assessments for every test you're allowed to run. And then test method validation studies. All right, so there's different phases of testing. So we have the patient. We cannot control the patient. They are who they are. So they have their own diseases. They have their own genetics. And then you have the pre-analytical phase, where you are collecting their specimen, hopefully correctly. You are transporting it, processing it, and storing it. So everything leading up to actually testing it is considered pre-analytical. So this would be like, a problem with pre-analytical would be like, oh, I left this sample in a hot car while I was eating my lunch because it's the summer, and that could mess with the sample. So especially like with courier samples. And then the analytical phase is anything where you're like physically testing it, including like the controls, the procedures, the technologists involved, any statistics. This is basically it on the instrument or in your hands being tested. And then there's the post-analytical phase, which is comparing it to the reference interval, any calculations you had to do. And then they have a little separate box here for interpretation. Usually interpretation is lumped in with post-analytical. Interpretation is basically where it gets to the clinician and they make medical decisions based on it. That is also outside of our control, but we can make sure they have an accurate reference interval to compare it to. There are some interesting case studies where the reference interval is wrong and people almost died. So that's important too. And then so all this leads to a result and decisions being made. So errors within the total testing process, the bulk of them happen in the pre-analytical phase. That stresses me out because usually I don't have control over the pre-analytical phase. So you're trusting it to someone else. So this is like when the incorrect test is ordered, heaven forbid a patient identification mistake, where you collect sample on the wrong patient. That's horrifying if you work in blood bank. The test request was lost, you lost the sample. I had a friend who was getting tested for like Huntington's disease and the courier lost the sample in her car. And it took several more months for her to get tested. So sample collection error, that it's not handled correctly, things like that. And then analytical error is about 7 to 13%, which that's the lowest one. So I'm like, kudos to us. We did a great job. So this is sample mix-ups, equipment failures. You don't catch a failed QC kind of thing. And then post-analytical, the test result got lost in the ether, got transcribed incorrectly. So some of these manual methods where you're physically putting in the answer, like the result into the computer, there are chances for error there. So this is why in our lab reports, what you put in your little box of this is my answer, that is me testing you don't make a transcription error. If your calculation is right over to the side and you have the right answer over there, but you didn't put it in the test result box, you're being graded on the test result box because that is what you are saying you sent to the physician. That is what is going to have medical decisions based on it. So that's why at least I am very anal about that is your answer. You're saying you have sent that to the doctor. Okay. And then the doctors come in and they either correctly interpret or they don't. We cannot control them. All right, so then we have our QC materials. So these are stable for a long time. And that's because hospitals like to buy huge amounts of it for the entire year or for like 6 months. Because every time you change lots, it's really annoying because you have to validate that lot and verify it. So these QC materials are often lyophilized. And you're like, lyophilized, what's lyophilized? This is a weird word. It's basically a fancy science way of saying freeze dried. So they basically suck all the moisture out of the serum or urine or whatever matrix the QC is in. So that way you can like add liquid to it later and reconstitute it. So it's basically freeze drying your sample. And then they make huge batches of these QC materials into lots or batches. So they have very minimal vial to vial variation because it's basically huge pools of samples that they've then basically checked to make sure that they're good. And they freeze dry it and aliquot it out. And like, here's your lot for the year. And it's important that it's in the same matrix as the patient sample. So a matrix is basically like, if I'm going to be testing this analyte in serum, my QC material is in serum. If I'm going to be testing it in urine, the QC material is based in urine. So, because there can be interferences unique to a particular matrix. So amniotic fluid, you look at an amniotic fluid matrix. Urine, you look at urine. Like you just want to keep apples to apples as much as possible. You test it at the same time or before the patient sample. And then you make these concentrations are usually at medical decision levels because that's where you want to be most accurate. They can be quantitative, meaning you assign it a number, or qualitative, meaning it's just a yes or a no, positive or a negative, depending on the assay. And then you can have assayed or unassayed concentration. So depending on the size of the lab that you're working in, you might have assayed QC materials. And that's basically where you're paying the company that has manufactured the QC material to measure the concentration of everything in it. But that costs more because the QC company is measuring it, right? You're having to pay them for their time. Whereas if you're a big hospital and you're going to have this QC lot the entire year, it is cheaper for you to buy the unassayed concentration and then assay it in-house, assay it in your lab and figure out what the mean is and all that. So some of it's just cost. If you're a small lab who doesn't run this very often, it's probably more economically better for you to buy the assayed one. So you don't have to waste reagent or in QC material assaying it yourself and setting up the QC ranges. So it's a lot of decisions in clinical lab comes down to economics. Yes. Yeah, sometimes there's a high, mid, and low. You're usually going to have at least 2 QC levels, a high and a low. You might have a mid depending on the assay, but usually you're going to have at least a high and a low. And then you have internal QC programs. And internal QC is what you run every day in the lab. External QC is where you actually pay an outside agency, usually CAP, and they send you samples throughout the year, and then you run them on your instruments like you treat every other sample, and then you send back your results to CAP, and they say, congratulations, you match what everyone else got. You're doing a good job. Or they say, you did not get what everyone else got, and that is a problem, so we're keeping our eye on you. And if you fail again, we're going to basically make it so you can't test for this analyte until you prove that you can do it. So they're kind of like the overlords, making sure that the labs are doing a good job compared to other labs. This is called a proficiency testing program. Which gets me is that you pay them for this, and then they judge you. You're paying someone to judge you. Just, yeah, I think it's funny. All right, so we're going to talk about some best practice. This is what we expect you to do in the clinical lab. So you want to reconstitute your QC materials according to the manufacturer's recommendations. So don't go rogue, read the instructions, do what you're supposed to do. If it says swirl it for 2 minutes and let it sit for 20 minutes before you use it, swirl it for 2 minutes and let it sit for 20 minutes. All right, use the appropriate volumes, do it at the appropriate temperature. Just do what you're supposed to. And then when you open a new bottle of reagent or QC material, you must include the following on the label: your initials, so that if something goes wrong, they know who to talk to. The open date, which i.e. the date you opened it and reconstituted it or do whatever to it. And then the new expiration date, because a lot of these things have a very long shelf life. Like its shelf life can be like 2 or 3 years. But as soon as you open it, you've now introduced the ability for germs to grow and for things to dehydrate and stuff. So it has a new open expiration date. And there's got manufacturers' guidelines on how long that open expiration date. Sometimes it's 24 hours, sometimes it's a month, just depends. And the key thing here, and this is something that a lot of students struggle with, your open expiration date cannot go past the original expiration date. Think of this like milk. All right, the expiration date of milk says it expires next week. If you open it the day before it expires, it still expires the next day. Okay? Like it's still going to go bad. So if you open a bottle of QC that expires in a week and it technically has an open expiration date of 1 month, it still expires in a week. It doesn't magically get a longer expiration date because you opened it. All right. So when you're picking your open expiration date, go with whatever date is soonest. All right. A lot of people struggle with that. Just want to make that clear. All right. So some QC material examples. This is what they look like in chemistry. So this is a LIFO check. You have levels 1 and 2. They make those nice and big. And they also have different colored caps. That's only as good as if you make sure the right cap goes on the right bottle though. Then you have some hematology ones. These are based in blood and whole blood, high, normal, low. You even have little gram stain ones to make sure that your gram stain's working. The urine ones are pretty fun because they actually come on these little dipsticks and you soak it in distilled water for like 30 minutes and there's analytes embedded in these little pads and they leach out into the liquid. And that's how you make your QC material and then you test it. I think that's kind of fun. And then you have things that are like qualitative. I think this is an ICTO test where you put a little tablet down and you put little QC material on it and see if it changes color. It's either positive or it's negative. These are really annoying to run in real life, by the way. It's really hard to tell the color difference. And then you have like a fecal occult blood where the QC is actually built into the pad. This is poop. And right here is your little QC box and you add your reagent and it should turn blue. If it does, that means your little filter paper that's embedded with chemicals is working. Then you have things that you actually do in-house, like this is a little catalase test. It should bubble when you add your little microorganism and add the hydrogen peroxide. I always think that's fun. All right, so QC testing must be acceptable and must be performed and deemed acceptable before patient tests are released. Because the QC is basically telling you, was there a problem? You don't want to release your test results and then go back and go, oh crap, that did not work. Because then you have to call the doctors and be like, I'm sorry, we made a mistake. And that makes us look bad. And it could be hundreds of samples that were affected. So always wait to release your patient results until QC has passed. You must record your QC data, even if it failed, because failures can tell us what went wrong. And then if your QC fails, you need to do some type of troubleshooting. Sometimes that's just repeating it one time and going, okay, random error, it just fell out that one time. Now it's back in, we're good. Other times it's like, something has gone wrong. I need to figure it out. And then you should never release QC before, you should never release your patient results before your QC has passed. All right, so one important note, only record what you do. If you didn't do it, don't write it down. If you did it, even if it failed, write it down. Your goal in life is to be able to drop dead in lab and for someone to know what you were doing and what you have done. Because that is essentially what happens at a shift change. You leave. You don't want people calling you at home asking, hey, did you do this on such and such a patient? You don't want that. So document, document, document. That way you're not getting called at home. All right. So when you run QC, you look at it, see if it passes. If it doesn't, you then look and you go, what is it telling me? What is the data telling me? And what can I take this data and help me figure out my troubleshooting? So we take a look at all this QC data and we track it over time and by lot to look for patterns that happen in the data. And these patterns, they can be called shifts where something jumps up randomly or jumps down for a long period of time. They can be trends where just kind of slowly eking down, or they can be biases, things like that. So you're looking for patterns to kind of go, what might have gone wrong? Because you don't want to just start shooting in the dark when you're trying to troubleshoot. That would take a long time. If you look at the data, it can tell you where you should start your troubleshooting. So control data is acceptable if it's within the established limits. So this is like for qualitative, that's positive, negative, high, low, yes or no. Semi-quantitative is usually like, is it less than this cutoff? Is it greater than this cutoff? And there's published values on what it should be. That's like a lot of the urine QC is like that. And then you have quantitative where it should fall within a lower and an upper limit. All right, so some lab lingo. So there are multiple ways to say something that QC has passed. We can say it's in control, it's in range, it's acceptable, it's passed. all good, you know, there's lab lingo. And then for fails, for something that when it has failed, you can say it's out of control, out of range, it's failed. For me, you say it's gone wackadoo, something, you know. So there's lab lingo they should be aware of. So for qualitative QT evaluation, we're gonna look at a little example here. All right, so this is a little log in the lab of an ICTO test, which I've told you is annoying to read. And honestly to set up, because you're trying to get this little droplet to fall off the tablet and it's stupid and it doesn't want to fall off onto the pad. It's really annoying. So we have our lot number and we have our expiration date. So we're good for expiration date. We can track it over time. We can see that KP at 5:16 a.m. it's positive. DGW it's positive. TLB on 8:20 at 5:17 it's negative. All right, she's like, okay, it's negative. I'll set this aside for a minute, come back to it. And so at 6:05, she tests it again, it's positive. And we're like, okay, it works, yay. DGW positive, KP positive, and then TLB comes back, it's negative on her first try again. So she waits a little bit, waits like an hour, comes back, tests it, it's positive. And 8:24, she comes in at 6:10, tests it, it's positive. 8:25, 5:11, it's negative. Repeats it at 6 o'clock, it's positive. What could be going on? Or it seems like only TLB is having a problem. The other technicians are doing fine. Huh? Yeah, so she's the system in this problem. She's the problem, yes. So TLB is the problem. So is there a pattern here? So anytime she does it at 5 a.m., it doesn't pass. When she comes back and does it at 6 a.m., it passes. How do you function at 5 a.m.? I don't function well at 5 a.m. Neither does TLB. So she's a little sleep deprived and out of it at 5 a.m. So she goes and drinks some coffee and comes back at 6 and it works. So for her, the best way to fix this was to adjust her schedule so she starts at 6. So she's a little bit more with it. And that fixed the problem. All right, so for quantitative QC evaluation, we have our Levy-Jennings charts, our LJ charts, and this is, you have the mean as the central line here. And then you have on either side, these dashed lines or blue lines, that represents one standard deviation from the mean. So this is this blue area. Then you have lines for 2 SD plus or minus, and you have lines for 3 SD. And what you do each time you run your QC is you plot where it is, like what value it is. So these along this y-axis are values. And you can just quickly look, is it in or out? So is it within this 2 SD or green area? And anytime it falls out of this green area, it's considered out of control or it has failed. And then you would look back at previous results to see if you can find a pattern of what has gone wrong. And there are rules to how you look at the data and what's considered a failure. Because remember, 95% of the time it should be within 2 SD, but 5% of the time it could just be randomly out. And no one wants to, you don't want to troubleshoot 5% of all your values. So this is an example here of a trend, because it is trending downwards. There's just this little gradual slope. It can be going up. This one's gradually sloping down. So this would be something where you're looking at something slowly changing that's causing this to creep down. So this would be like your reagents deteriorating, your QC is deteriorating prematurely. This is where you can look at different levels of QC. It's like, is it only affecting one level? Is it affecting both levels? If it's affecting both levels, you're like, okay, it's probably something with the instrument. If it's just affecting one level, it's like, okay, it's probably something just with that one level. Then you like make a new like vial of it. Whereas with shifts in this one, we have just randomly jumped up. The mean has now changed starting at day 13. Why did it do that? Something has abruptly changed. This is what a shift is, where something has abruptly changed. So this could be you put in a new lot of reagent or QC and didn't document it and didn't set up new values. This could be you added in a new light bulb on your spectrophotometer and it's brighter. Or it could be you trained a new technician and now they're taking over on that shift and they do it differently. So all these things can cause a shift. All right, so in summary, error is unavoidable. And there will be more information about QC stuff in the actual dry lab you're doing today. So make sure you read the actual stuff I wrote. It's informative. Don't just ignore it. So error is unavoidable in the lab, but should be minimized wherever possible. Accuracy, precision, and reliability are important parts of ensuring quality laboratory results. And this is something that you figure out when you're validating your assay, when you're first setting up, you go, okay, how accurate is it? How precise is it? There's a lot of statistics involved. What's really nice now is that a lot of companies, because everything's like automated instruments, the companies will have someone come in and validate it for you, which is nice. But then you also have lab developed tests where you have to do it yourself. So it's still important to know. Some people really enjoy validating. I like validating. It makes me happy. I get to use Excel sheets. If I get to use an Excel sheet, I'm happy. They also have special software to do validations. EP Evaluator. It's not great. Doesn't bring joy like Excel does. And then you have quality control and quality assurance. They're not synonymous. So quality assurance is like the overarching umbrella that quality control falls into. So quality control is a component of a quality assurance plan. It's basically little soldiers on the ground making sure it's working. The plan is working. And then a good quality assurance plan includes QC testing, equipment maintenance, a safety program, staff training and competencies, written policies and procedures that include specimen collection guidelines. That's only as good as the people up there actually collecting the specimen. So you might have to do training of the people collecting specimens. And then participation in proficiency testing and laboratory accreditation. All right, so you should have stable matrix matched control materials at clinically relevant concentrations to test the reliability of your test method prior to releasing patient results. And you want to make sure that you evaluate your QC results for patterns that can help identify problems and focus troubleshooting on the most likely problem. Because if it's a trend, you're going to look at something that might be more system-wide or just at that particular QC. So you can basically look at your data overall and kind of figure out what is the most likely error that's happening so that you're just not shooting in the dark trying to fix things. Because if QC fails, it takes it can be really annoying, especially since on a chemistry analyzer, you can have hundreds of assays on a chemistry analyzer. You're measuring multiple levels of QC. So you're essentially measuring, say, 500 assays to get QC to pass. And if 5% of the time it can just fail for random chance, that's a lot of tests that could fail on any given morning. And that's what happens in the chemistry lab. So you don't have time to just randomly shoot in the dark every time there's a problem. So if you look at the data, you can figure out where your troubleshooting should be aimed. So it takes way less time. So that way you can get patient tests actually going through and getting resulted and sent to the physicians.